In the previous video, we had a look at the different data types. We also loaded the data and the respective libraries. So have a look at those videos up here somewhere. In this video, we're going to be looking at dealing with incorrect or unwanted observations. So let's jump straight into it. So if you look at the data over here, following on from our previous video, we ended off with looking at the data type in terms of the describe function, .describe function, specifically the categories. Now let's look at dealing with incorrect or unwanted observations. So let's run this line of code over here. And what I've done over here is I have checked whether the columns have any value other than numeric. So the output shows that every single row in the data frame has some non-numeric value. The next line of code is now, we've noticed that there are some variables. If you look at the data frame, there's an @ sign, there are three $signs. So what I want to do now is I want to ask Python to identify specific symbols that I believe are in the data, that it should highlight it for me. So I give it this line of code over here. Now you define the symbols, so symbols to identify equals square brackets, and then I identify the respective symbols. You can see @ sign, the hashtag, the percentage sign, if there is, the dollars, the $3, the $1, the and, the asterisk, maybe a full stop, a period, a /, maybe a comma. I mean, you can list whatever symbols you feel there might be, and you can make that list longer. I decided to only do these. So you can see I generated the code, and there was no output, but the 23 is indicated. That means it has actioned the code. If I just scroll up a bit, now what I'm going to do is I'm going to ask it to print the symbols to identify, just so that I know that Python is going to look for those specific symbols that I've identified. So that prints it, it has actioned your instruction in line or input number 23. So now what I'm going to do is I give it this code, and what this code generates is it goes through every single cell of all the rows, in other words, the entire data frame, and it tells me specifically where there is an identified symbol that you stipulate in the code up top here, and in what row it is, and in what column it is. And then it indicates the value. Now, you must be very careful now, because you might be sitting with a data frame that has 150,000 rows. If you ask it to look for a string with a period or full stop, and you are sitting with a column like economy rate, where every single cell will have a period in, because it will be 3.14, it might be 4.9, it might be 10.3, whatever. All of them have a period. What it's going to do is it's going to generate, or it's going to highlight every single one of them. You can see that's what it's done. Look how many periods there are if you go down the actual output. So be very careful. You would expect then that the period would be in certain columns. So maybe it's not a good idea to include it in a search or a generation of code like this. But if you feel you need to do it, then you can do it. Now, something like the / would also apply in this case, because there are bowling figures, 6, 4, 32. So assuming that all the bowlers that are bowling have a best bowling figure in an innings or a best bowling figure in a match, there would be a /. So again, it's going to list every single one, depending on how many there are, it's going to list them all. So the more interesting ones might be something like an asterisk. And we know that the column highest score would have an asterisk, and I can see a 278 asterisk. Now I know that that figure is AB de Villiers' highest score, 278 runs, and the asterisk indicates not out. All of the highest scores in terms of the HS column, highest score, would then have asterisks, which means that it would not identify as a numerical data type, which means the entire column will not identify as a data type. So we have to think of maybe separating the asterisk from the value somehow. That's something to keep in your memory bank again. So we can go down, we can go down, we can go down. A lot of numbers with periods, a lot of numbers with /. And as we go right down, you'll start seeing every now and then there's something like $1 right at the bottom. There are 3 cells that have either an @ $3 or $1. The first one with the @ is in cell 124 in row 124, and it's in the column balls. And then the $, you can see exactly what that is. So do that to get a sense of how dirty your data is. You're going to have to fix that. You're going to have to delete those symbols. Otherwise, you cannot do visualizations or analyses for those particular columns. So why would you not do it? You have to do it. So the next line of code, what I want to do is I want to then potentially split values or cells in particular columns. We use the parse function for that. So in our case now, BBI, best bowling in an innings, you would have a value like, as I indicate up top here, 2 for 23, 6 for 47, 1 for 19, 8 for 32, whatever the case might be. Instead of keeping the column best bowling per innings, let's split the column into the number of wickets and the number of runs. So what that does is it circumvents the fact that the column BBI is an object data type, and it splits the variable or the cell value into the number of wickets and the number of runs. So you've still got the data just in different columns. But now you notice when I ran the code, there is an error. And the reason there is an error is because there are missing values in the data. So what we need to do then is we need to run an adapted code, where what we've added is this line of code over here, where we are handling the NaN, not a number values. But you can see there's another error, and it's good to have these errors that you learn out of them. And if you look at the error message over there, it indicates that some cells might have a white space in it. Now the white space is a problem because Python picks up that white space. It must be exactly uniform in every cell, in every column, in every row. All the expected values for a column should be uniform. All the expected values for a row should be uniform. So we're picking up that there are cells with problems. If it's not a symbol, it might be a white space. If it's not any of those, it might be a missing value. What we then need to do then is address that as well. So what I do is I add this line of code that also takes into account over here, in this part over here, the white space. So this parse function, you'll see that it is indented. So if this happens, then you need to try splitting it, except if there's an error. So let's see what that actually means. We run the code, and look what it's done here. It lists all the variables, the rows, from Andre null, but you'll see it doesn't go to the right. In fact, what it does is it continues underneath. The value for Andre null, A null, is row number 0. So row number 0. The ducks, the zeros, and the hand bat for Andre null would continue over here. And then if you go down further, for Andre null again, it would continue over there. So he was a medium fast bowler, right-hand bowler. And what you'll notice is now, if you look at his best bowling in an innings, it's 6 for 32. But what this function has done here, this line of code, or these lines of code rather, it has split that value of 6 for 32 with the /, which is a string, and it's split it. Wickets, 6, runs, 32. So now you've got 2 additional columns that have split those values. And if you look at the second cricketer, who is Anrich Nokia, if you go down to his values over here, his best bowling is 6 for 56, 6 for 56. Now I know, this was one of my favorite cricketers, the value for 8 for 71 is Alan Donald. And I know that because he's taken 333 wickets, and if I'm not mistaken, it's in 72 matches. So you see, constantly I'm checking my data, because I know this data. From a fan point of view, I've got an extra dimensional domain knowledge, very important domain knowledge, attached to this particular data because I am a huge fan. The domain knowledge that you might have in your work environment will be attached to what your work requires. Right, so that's good now. But now the problem is that there are a few things there. But let's just look at the next line of code that I give you. Notice now that there are 27 columns. Now, that makes sense because you split the BBI, best bowling figures per innings, BBI, into 2 additional columns, being wickets and runs. So the number of rows haven't changed, but the number of columns have increased by 2. As I mentioned just now, they are listed at the end, and that doesn't make sense. You don't want it to be listed at the end. Why would it be at the end? It's going to confuse you. What you want it to be is you want it to be right next to the BBI figures. You'll notice here there are hashtags in front of the lines of code. If I run it, nothing's going to happen because it reads it as an invisible comment. What we want to do now is we want to move these two columns over here right next to BBI. So you do that with the index get lock functionality within Python. BBI index, so you're going to index, in other words, find exactly where the column is, and you want to look at specifically BBI. So you want to insert wickets, there's wickets, and you want to do it right next to the BBI column. You want to do the same for runs. So if I generate this, look what it's done. If you look at BBI, next to it, wickets, runs, and it's not at the end anymore. So it has moved those two newly created columns right next to the BBI. What you're going to expect now if you do a data type print function, you're going to see that BBI is listed as a data type object because of the /, but the wickets and the runs respectively will be listed as numerical, either float or integer, or rather it can be converted into either a float or an integer. But have a look at the bottom here. There's a missing value. That could create problems. There are missing values at the bottom. We are not finished yet. We've done that now for BBI, and we've created an additional 2 columns which allow us then to analyze this in more detail. But now there's another issue. If you look at the names that we gave it, we gave the wickets column the name wickets, but there is another column called wickets. It's just abbreviated. That's confusing. The runs column, which is the runs indicated by the best bowling per innings, the runs over here is for that individual best bowling figures, but there are other runs attached. Runs scored, might even be highest score, etc. So the naming of that needs some adaptation. Let's then convert those names to BBI underscore wickets, BB underscore runs. So then you know it's the best bowling per innings wickets and the best bowling per innings for runs. We do that with this code over here. It runs it, and you can see that it's changed the heading names. So if you look at the actual code, we want to identify the index, right? And then we're going to insert in those particular columns, wickets, we're going to change it to include the BBI underscore part for respectively the BBI and the runs. And then we're going to print it. So that's done. So that's great. So let's print all of those outputs over here. You can see now that if I print BBI, it lists it like that. If you print BBI wickets and BBI runs over there, it lists it like that. If you print all 3 together, BBI wickets and BBI runs, it lists it like that. So that's a nice way of depicting the actual values in those respective rows and columns. So now the question becomes, we've done it for best bowling per innings, but what about best bowling in a match? It's the same situation because you can have a best bowling per innings of 6 for 32, but the best bowling per innings can be 6 for 32, it can be 11 for 47, it can be 19 for 99, it can be 2 for 3, whatever the case might be. So we need to do the same for the best bowling per match. So here's the code over here. So it's the same code that we run up there. And then what I've added at the bottom here, this part down here, is the part where I add the best bowling per match underscore to the respective runs. So you can add the 2 lines of code that you did up top here, line 32 with line 30, you add them into 1 line of code, and it does it sequentially. So if I run this code, there it's done it all in 1 click, 1 shift return. If you look at it, there's best bowling per match. Now I've split it, and I've added the underscore best bowling per match for the wickets, and I've added the underscore best bowling per match for the runs. So again, the best bowling per match, the BBM column, will be indicated as a object data type, but these 2 columns will be indicated, or can be converted rather, to either float or integer columns or data types. Let's print a sample of the BBM column to get a sense now. Like I did up top there, BBM on itself, the head, the first 5. I'm doing the same for BBM wickets, BBM runs, the first 5 head. And then I'm doing the same for all 3 of those, the head. So you can get a sense there. And that corresponds to what we did per the figures for best bowling per innings. So this output over here, what I've done is the same as on top, where I want to identify the different symbols. And again, we've got a situation with all the full stops, the periods, we've got forward slashes. If I go right down, you'll see at the bottom here, there's the @ sign, there's the $signs, 3 in a particular cell, 1 in a particular cell. You would expect this. Now let's consider the columns with a period. There are 4 of them. We know average bet, average bowl, economy rate, and strike rate. The question then becomes, if I've asked the code to identify these cells with periods, should I split it like I did up top here with the best bowling figures per match and per innings? Does it make sense to split a cell where the value is, for example, 2 for 27, just like you did with the best bowling figures? No. Because what does it mean? 2 and 27. It means nothing. You cannot split, for example, the strike rate. If the strike rate is 43.55, the 43 and the 55, respectively, separated, mean nothing. It's not like the best bowling figures where you have 6 for 32. 6 wickets for 32 runs. The 4 variables that are regarded as floats, average bat, average bowl, economy rate, and strike rate, they will have decimals. So it doesn't make sense to split them. What we rather need to do is we need to regard those columns as float data types. Now you see, if I did not have an understanding of the data and I did not understand cricket and the meaning of the values and the stats and the interpretation thereof, there's a good chance that I might not get to that conclusion. So domain knowledge is essential. You, as the analyst, should have a sense of the domain knowledge. We are therefore not going to split average bat, average bowl, economy rate, and strike rate. It makes absolutely no sense. But there are other cells that have unwanted symbols, as we indicated. And I remember they were at the bottom somewhere. There's the @ sign, and there are the $ signs. So there are some problems here. So let's do something to get rid of them. So I'm giving it several lines of code here. The first one is to give me the describe statistics. You can see them over there. Lines 4 and 5, or particularly line 5, identifies the missing values. There are the missing values. And then this line 8 over here tells me how many values are unique. And then I print these words, those words, those words. Let's have a look at those outputs. In terms of the summary stats, now notice it is only going to list the numerical values because you can't do a mean or a standard deviation for a string value. Python only identifies matches, innings bowled, runs conceded, wickets, economy rate, and 10 match as numerical values. And that's a problem. But you can see here the count for each of them respectively, the mean, the average, the standard deviation, the minimum value, the 25th percentile, the 50th percentile, the 75th percentile value, and then the maximum value. We know that there would be cricketers that have only played 1 cricket match, 1 test match. We also know, I know, my domain knowledge knows, that there is 1 cricketer who's played 165 test matches, and that's Jacques Kallis. So the range there, min-max range, is correct. In terms of innings bowled, I know there would be a bowler that has bowled in 1 innings. In terms of 270 innings, I can't tell you who that is, but that doesn't sound unreasonable. In terms of runs conceded, 1 is the minimum, and the most is 11,242. So there are a few cricketers or bowlers that would be. In terms of wickets, you would expect 1 bowler not to take any wickets. And the highest number is 439. I would expect that because I know that is Dale Steyn. In terms of the economy rate, the lowest is 0.5 runs per over. And the highest is 8 runs per over. I can't tell exactly who that is, but that's not unreasonable. In terms of 10 wickets in a match, you would know that there are cricketers who've not done that. But you also know that there are cricketers that have done it. In fact, 1 cricketer has done it 5 times. In terms of the missing values, yeah, you can get a sense for the missing values. There are none in these over here. But once you get to look at these columns over here, notice they are the bowling columns. So there are missing values in the bowling columns, which you would expect, because not all the test players would bowl. Some are wicket keepers and some are just not good bowlers, therefore they don't bowl. This is not unreasonable, and the numbers attached to them don't seem out of sync. There doesn't seem to be an outlier that is dramatically larger or smaller, well, not necessarily small in this case, but way out of sync with the other cells. There doesn't seem to be anything odd in this case now. So let's look at that minimum maximum again. And yeah, it just reiterates what we had anyway in the column up here, just in a shorter format. It's always good to have these different types of code that you can use whenever you need them. The next line of code, let's see if we can visualize anything that might be odd. So what I've done is I've highlighted only these numerical values because only those columns over here are regarded as numerical columns, which is a problem, remember? And I've got a box plot. And you can see with a box plot, there are quite a few outliers. But it's not odd. There are cricketers who have scored more than 10,000. Quite a few that have scored around 10,000. Your A.B. de Villiers', your Graham Smiths, and then in this range of say 6,000 to 10,000, there would also be a few. You would include players like Hashim Amla, Gary Kirsten. By far, most of the cricketers are over here, especially the median of cricketers. So there's nothing suspicious in that regard. So the next line of code here shows, again, I'm listing this same code as above in terms of the symbols. But now remember, what we've done is we've dealt with the forward slashes. The forward slashes were the best bowling per innings and the best bowling per match. And we've split them. So we don't have to worry about the forward slash anymore. So you can see in the next line of code over here, if you look at the symbols to identify, I name it 2. So it's the new placeholder. And I'm including these symbols, and notice I exclude the forward slash. So let's run this code over here. It's run successfully. There's no error. The number shows over there, 42. Now I'm going to do exactly the same. I want to see. I also omitted the full stop, the period. So I've omitted the period and the forward slash, which excludes the columns best bowling per innings, as well as best bowling per match. And it also excludes the economy rate. It doesn't make sense to include economy rate and split them. What is left now, excluding the period, full stop, and the forward slash, are only these symbols over here. Can you see how we've reduced the number of unwanted cells in terms of these unwanted symbols? There's hashtag at dollar, at $3 and $1. And that gives us specific indication of where they are, so you can know exactly what they are. So now we've got a more manageable data set in terms of funny symbols in respective cells. This line of code indicates that I'm going to replace the unwanted symbols with a missing value, because we can treat missing values rather than a 0. Because if you change certain values to a 0, it could mean something. For example, if there's a missing value in the economy rate, econ rate column, then it means that you are assigning an economy rate of 0. Which is possible. But actually what you are doing when you're giving it a 0 is you are trying to give it a value so that you can, in this case now, delete the unwanted symbol. So assigning a 0 makes no sense. So rather assign it a missing value. So I've given you a few other examples over here, but if you look at the data up top there's only these 5 or 6 examples over here. So I run the code, it runs successfully, and then I go back and I run that code again. There's no output. So previously where I got this output over here, there's no output. That means the output suggests there are no more unwanted symbols in your data, which is great. So if I go back to your tail, the last 5 variables, remember at the bottom here, we can distinctly remember there was an @ over there. For one of these variables was an @ and there was also a $3 sign at the bottom here. It's gone. So there are no more of these funny symbols in your data. That's great. You are slowly but surely applying these pre-processing techniques and getting your data clean. It's a slow process. Just as a side note here, what I indicate to you is the difference between a not a number, missing value, as well as a NA. So just have a look at the difference between that so you know they have different implications in terms of how you interpret them and analyze them. So that's for this video. In the next video, we will be looking at how we deal with missing values.